Hi everyone, in this video I'd like to start working through finding limits algebraically. So we've already looked at finding limits graphically, just looking at the graph and seeing what our y's are getting close to. Finding limits numerically, so we just plug in values really close to the x value we're interested in, and we see if we can find some sort of trend in the y values towards a specific number. So finding limits algebraically is going to be interesting when we have some sort of discontinuity. So our function is undefined at a specific x value, but we think we can use algebra to remove that discontinuity. So they're called removable discontinuities. This is things like holes in a graph. And then once algebra has removed it for us, we can see what our y value gets close to. So I'm just going to jump right in here. So let's look at the limit as x approaches 2 of x squared minus 4 over x minus 2. Okay, so again, if your function is continuous at x equals 2, this becomes kind of boring. You can just plug the 2 in, and whatever the y value is, that's what the nearby y values will be close to. Uh-oh, I'm doing a nighttime record again. I'm gonna start yawning. So here, I definitely have discontinuity at 2. If I plug in 2, the bottom is 0, which is a bad sign. So then the question becomes, is that 0 in the denominator causing asymptotic behavior, or is it really just a symptom of the fact that there's a hole in the graph? If there's a hole in the graph, we might get some nice finite value for our limit. If it's asymptotic behavior, the limit's either going to not exist if one side's headed to positive infinity and one side's headed to negative infinity, or it's going to be infinite. So in this case, the way to figure that out is to say, okay, the bottom is 0, the top, okay, let's be really careful how we say this. The bottom is approaching 0. We aren't actually letting x be 2. We're looking at x really close to 2. And then in the top, if we have x really close to 2, then this is really close to 4 minus 4, which is another 0. So the top is also approaching 0. This means we might actually have the hole in the graph and not the asymptotic behavior. So that's a good sign for finding nice values for limits. Okay, so to use algebra to help out in this situation, really what we're trying to do is cancel out the thing that's giving us trouble when we try and plug this number in. So the thing that's giving us trouble is this x minus 2. I can't have 0 in the denominator. So I would like to cancel that out, which means what I need to do is try and factor the numerator. And this looks like it's going to work out beautifully. There's that both the top and the bottom are 0 when x equals 2, and it cancels out, and I get the limit as x approaches 2 of x plus 2, which means that I'm getting that this whole limit is 4. So if x approaches 2, x plus 2 approaches 4. Okay, so that's the step-by-step through the limit. Nothing too crazy, just try and cancel out the problem. But I want you guys to be really clear on what's going on here. So what we're saying here, this step right here is really key. The only reason it's okay to say these two things are equal is because the limit's on there. It would not be okay to say that x plus 2 times x minus 2 over x minus 2 is equal to x plus 2 with the limit. So this is a no. But it's a small no. No, we wouldn't claim that those two are exactly the same thing. But what's going on is that this one looks exactly like x plus 2, but there's a hole in the graph at 2. So if we sketch y equals x plus 2, uh-oh, my blue pen might be wearing out on me. We'll try, I've got enough on. Okay, so if this is y equals x plus 2, the only difference between that and the graph of this ugly, messy fraction is that the fraction would have a hole in the graph. So here, I should be careful what I say here. So if we really want it to be the graph of this thing, It looks just like y equals x plus 2, but at 2, 4, there's a hole in the graph. So this is the graph of the fraction, whereas the graph of this side over here is just the line without the hole. So the only difference between the two is this hole in the graph at 2, 4. So yes, the limits are going to be the same because that doesn't change what your y values are getting close to, but they aren't actually exactly the same function. One has a domain restriction. Okay, thanks for watching.